many colleagues like Wei-Cheng Ye, Daniel Gottsman, Jiwen Liu, and it was published in last year in Nature Physics, like in 2024. So yeah, I mean, it seems uh, like Jinmin has been looking at quantum error correction from condensed matter perspective, and in this work, he has some nice study related complexity and order, study of that in approximate QEC, which is, one can say, it's a budget friendly QEC. So yeah, Jinmin, the stage is yours. Maybe you can start. Like, thanks
Yeah.
again. Yeah.
Yeah, thank you so much, Kishore. It's my pleasure to be here, and so I'll be glad to talk about my work about the complexity and order in approximate quantum correcting codes, and feel free to interrupt me if you have any questions. The outline of the talk will be as follows. So first of all, I will talk about the approximate quantum correcting code, what it is, why do we care about that, and how we can quantify that. Later, I will talk about our main results, like the relationship between quantum circuit complexity and the AQEC. More precisely, I will talk about the phase diagram for the AQEC codes. I will talk about how the capability of the AQEC codes can provide you a proof technique for the circuit complexity. And then I will talk about how this can offer you new insights in physics, both in the setting of topological order and the conformal field theory. So first of all, as all of us know here, the quantum error correction is very important in quantum QI science and technology. Also, it's very interesting that the QEC can also play fundamental roles in frontiers of physics. In many-body physics, inspire the whole community of the topological phases and topological order. Also, it was shown recently that the QEC property is related to the scrambling and thermalization of some condensed matter systems. Also, in the field of quantum gravity, it's known that the QEC can provide you a lot of insights in terms of holography and black hole information problem. But most of these are done for like exact codes. The basic idea of the quantum error correcting codes is that you just encode the logical information to a subspace of a larger entangled physical system, and the subspace is just considered of the code. So normally people just talk about the exact QEC codes. This is basically because the stabilizers are so good to deal with that it has a lot of nice properties. And by saying that the stabilizer codes are exact codes, we are talking about the no colloids and mathematical rigorously. We are saying that after this encoding and applying some no colloids, there exists the perfect recovery channel that brings everything back to the logical identity. However, the physically arising codes are widely important, but they are almost never a stabilizer or exact codes. So after all this process of noise and recovery, there's some residual error with respect to the logical identity. So this urges us to study the approximate codes, but the understanding of the AQEC codes are still scattered, and there's no systematic understanding. And I think our work just provides you a systematic way of understanding the whole thing. So to begin with, why is it necessary to talk about the AQEC codes? The first reason that as I told before is that there are always some practical deviations. So for example, there are some imperfections when you prepare the system. There could be some defects and disorder, so that the code that you prepare is like slightly away from the stabilizer case. There could be other cases in physics where we want the QEC to offer some insight to, and the code from the physical system sometimes can have inexactly just fundamentally originate from their physics. This will be later discussed in this talk. Also, we know that there are some fundamental incompatibility with the system, with symmetry. For example, we know that if the codes have continuous transversal logical gates, it can never be exact code. There will always be some fundamental inaccuracy. This is known as the approximate Easton-Neal theorems. The AQEC code is not only practically relevant, it's also interesting. For example, as Kisha just talked about, the AQC can offer you some advantage, like the budget is lower. So actually, it's shown that for specific noise models, the AQC code can outperform the exact code in various aspects. For example, you can have higher rates and higher distance. It was shown by Debbie Nunn and others that for amplitude damping noise, the code rates can be much higher. And also, my recent work shows that if you consider some certain kind of approximate code for amplitude damping noise, the performance can be way better than previous known codes. Sorry. And also from the QI perspective, the series of general codes and exact codes are somewhat detached. For example, if you just announce some extremely small deviation from the exact code, your system can actually have decoding radius to match code distance. So this is drastically different from what we know for the QEC codes. So I talked a lot about the approximate code, but what's the mathematical difference between the exact code and AQC? First of all, as I had told before, for the exact code, there is a full recovery of the nautical information. On the other hand, for the approximate code, there is only a partial recovery of the nautical information, so there will be some small epsilon here. Also, for the exact code, we know that the number of correctable erasure errors just gives you a clear notion of the code distance, because the correctable erasure error will just have a number of d-1, right? On the other hand, for the AQC codes, we know that the AQC can only correct any error approximately, so there's no clear notion of distance. So to describe this difference more carefully, we recall that in the literature, people have defined the QEC inaccuracy. So the QEC inaccuracy is defined by considering the encoding and the noise channel, and you just minimize over all possible recovery channels and see how different it can be from the nautical identity. The intuition of this definition is just the closest that you can get to the original state after the noise and the recovery. So similar to the exact QEC, to get a notion of distance, we just need to characterize the inaccuracy for different numbers of erasure errors. And this is why we will only focus on erasure error as the main error model that we talk about in this talk. And this will be made more precise later. So all this seems good, but there's one small problem with the previous definition, which is that we didn't have any restriction on the encoding channel. So this is basically saying that we can call any 2 to k dimensional subspace of an NQB system as an NK code. But of course, not all such subsystems are non-trivial or interesting codes. So how can we classify that? A conventional answer to this is that we just say that the code is non-trivial if epsilon goes to 0 when n goes to infinity. Here, epsilon is just the AQC inaccuracy. So this is basically saying that there's no logical information loss in the larger limit. However, there's a trivial case that can also satisfy this. For example, you just consider encoding as in here. So we consider some logical state, and we just append nodes of garbage that's perpendicular to original logical states. So now if you just consider a random noise acting on some side of the whole code state, with a high probability, the noise will just be thrown to the garbage state, so it does nothing to the original state logical state side. So actually, you can show that this case can also have a vanishingly small AQC inaccuracy in the larger limit. But of course, you will not say that this is a good AQC code. This is just telling you that we need more careful classification. So we need to have a more clear understanding of what kind of things can be think of as a good code or a bad code. To classify this, we just introduce a measure of AQC capability. This is called the subsystem variance. So here's a lot of things that we need to unpack. But the subsystem variance is defined as a function of the adjacency graph G, the code subspace, and some generalized notion of D. So here, epsilon is defined as the maximal distance between psi s and gamma s. The psi s is the reducing matrix of some code states on subsystem S, where the gamma is just the reference state. So it's a maximally average of all different kind of code states as the forms of basis of the code subspace. So basically, the gamma is just the logical is the maximal mixed state of the whole logical space. So here, the S is just a subsystem collected on G with size no larger than D. So G is just an adjacency graph, and D will offer you a generalized distance. As an example, we can just consider the case where
Sorry, Jinmin, can you go the previous slide? Where you had all this, yeah. So you're saying that you have this new quantity subsystem variance,
yeah,
and you are trying to look at like whether in the trace norm how close it is to like on the logical space to maximally mixed state. So
yeah.
so you look so basically you choose some subsystem, and that subsystem I mean you like you put some bound on it that it should not have some size larger than D, like I mean which you have according to some graph, like which still I don't understand. But you are saying that you so then you look at the overall state is, let's say, psi, and then you look at its reduced state, and then the reduced state how close it is to the maximally mixed state. And
yeah,
but then for that one is to ask which subsystem we select, and how do you define the graph G, which I think you will tell later maybe. Okay.
Yeah. I would. It depends on the notion of locality, which is denoted by the adjacency graph D. I will talk about this later, and it also depends on the distance. So later we will see how this is collected to the previous notion of the exclusive accuracy. You can find that. Yeah.
And you have that C is basically the code space, right? That is C, like I mean that fancy notations. Yeah, that's the code
space. C is just a code subspace.
Code space. So you take any so you maximize over all possible psi. Oh God. Oh, that can be like in practice this number can be difficult to get, right? I mean because like it's
I would say that it's, in practice it's actually easier to get than the existing accuracy, because here we are only maximizing over all of the states in the code subspace. On the other hand, for the existing accuracy, we need to maximize over all kind of recovery channels. So in that case, you need to like minimizing over a channel, which is pretty hard. But for this case, for example, if you consider the K, the logical subspace to be very small, this is easy to get. Even if K is larger, in certain scenarios, it's still computable.
Okay. Yeah, no, I was just thinking like in terms of complexity. Obviously, like both are. I mean, that is also a hard problem, and yeah, but maybe like this is less hard. But I was thinking, because a set of psi, like they are pure states that will form a like a non-convex set. And because of that, like it may be hard, but it could be less hard than like optimizing over the recovery channels. Yeah.
Sorry, I don't think I get it, because here by convexity it's easy to show that this maximum can always be taken when psi is a pure state. Although even if psi s by itself is not a pure state, this maximum is always taken for some pure logical states. Is this what you're asking?
No, what I'm saying is, your maximize over all possible psi, right? And the set of psi basically is like so all your psi in the code state, they are like you consider pure states, right? I mean, you optimize over pure states. So if you optimize over just pure states, then mixed states are not in the optimization.
Yeah.
So basically, if you take two pure state, take their convex combination, that's not in the feasible set.
No, it's not.
And because of that, like non-convexity leads to issues like local minima problem and so on, and the optimization becomes difficult.
Oh, but that is not actually an issue, because here you can just change the definition of epsilon to take psi to be any mixed state in the code
Okay,
subspace.
if you take anything, okay, then you can take the like the entire hull, and then like when it's fine here. Okay.
Yeah, it doesn't change anything. So so let me move on. So as I just said, this just measures the no code distance between any code state and the maximum mix of it. So as an example, we can consider the urgency graph on a 1D chain. So here we consider the case where D equals to 2. So the urgency graph is just telling you that the S can be 2 local subregion of the whole 1D chain. So it's something like this. So, and the intuition of this is just the amount of information that you can get from the code locally. This is because when psi S is exactly equal to gamma S, this is telling you that any local measurement cannot distinguish any code states with the maximum mix state of them. So of course, since you cannot distinguish them, you cannot never get the information from there. So even if you just throw away the whole subsystem, no information is lost. So Epsilon just gives you a quantity of like how many information the erasure error can erase from the system. So one thing that we want to emphasize is that our work is works for general G, like the urgency graph, but here in this talk we will just focus on 2 cases. One case is when the urgency graph is a lattice system. In this case, the S will just be local on the lattice, so it's some geometrically local region. On the other hand, we can also talk about the case where G is the G has an all-to-all collectivity. So in this case, the S will just be any set of qubits with size no larger than D. It can be scattered, and 2 different qubits in the region S can be non-collected or anything.
So basically, Jinmin,
Yeah.
sorry, because this is an important part that so basically what you are saying that, you start with an adjacency graph, and then you have this notion of, I mean, you have this code space, and then what you say that, you fix a region with, size at most D, and on that space, you look at, what is the effective, reduced code state, and how far it is from the maximally mixed state, the logically maximally mixed state.
Yeah, exactly.
On that S. And what is the intuition, why did you define this quantity? Will you talk about it later, or you are already done? If maybe you can just give a bit of intuition,
Yeah, I think the core intuition is just here. The core intuition is that I'm measuring the difference between a code state and their maximum mix state on some region S. So in the extremal case where epsilon is just 0, this is telling you that psi S is equal to gamma S. So this is so if you consider any observable on region S, you calculate the expectation value of that observable. You'll find that the expectation value will be the same for psi or gamma. That will basically telling you that for any state in the code substrate, the expectation value of the operator O will be the same. So this is telling you that for any local measurement on the region S, you cannot tell the difference from any 2 code states. So since you cannot tell the difference from for any 2 nautical states, you cannot get the information of which nautical state you are in by a local measurement. So this epsilon measures like how different the local measurement can be for different nautical states. So it basically tells you the amount of information that you can get by doing a local measurement on the region S. So if you can get some nautical information from a local measurement on region S, that means that if you erase S, there will be some nautical information loss. So when epsilon is exactly 0, you do an erasure on region S, no nautical information is lost. That basically means that the code will just be an exact code. When epsilon is small, this is just the approximate code. You can get some information, but not all of them.
Okay, very nice. By the way, this subsystem variance can be generalized. I think Andrew can also maybe say something. So this subsystem variance, so basically we had recently this paper on approximate locate codes. And there basically what happened that your code space, it changes over time. So you have one code space, then you have another code space, then you have another code space. But you can talk about the same thing, it's just that instead of psi being to code space, you can also maybe take a union of code spaces over all these different times, maybe, or maybe what you can do is that you calculate the subsystem variance for every code space and then take the maximum of all, or I don't know, maybe minimum or so so basically what I'm saying that instead of one code space, the only thing that changes there is that you have multiple code space, and in flowcate case you basically come back. So I think one should be able to generalize it for the flowcate case. Anyway, let's talk about it later.
I will just leave a remark here. I feel like it's easily generable to the flow case. The only thing that you need to change is just add an argument T here in the definition of subsystem variance.
Yes.
So for psi s will depend on T, gamma s will depend on T, and I don't want to maximize over T. I guess the ideal case here is just that the epsilon turns out to not be depending on T. But I'm not so sure whether it holds. But I guess if you add the argument T here, epsilon will still give you a notion of approximateness in that case. Yeah.
Basically, you're saying that it's like for different steps, like there will be a different subsystem variance. Okay.
Yeah. For different times, there will be a different subsystem variance.
Very nice. Thanks. Yeah. Very nice.
Yeah. So I talked about the subsystem variance. There are a lot of intuitions there, but what exactly it means for like quantum information properties? Actually, you can find that the subsystem variance is two-way bounded by the QEC inaccuracy, as I defined before. More precisely, you can find that for any noise given by replacement channels just includes like erasure, reset, or complete depolarizing channels. You can prove this two-way bounded between epsilon, which is the subsystem variance, and epsilon tilde, which is the QEC inaccuracy. More precisely, you can notice that I didn't write down the arguments N, E, and the adjacency graph here. But for the case of adjacency graph, it just gives you the notion of locality for the replacement channels. For example, if you consider the lattice systems, then this is telling you that you need to consider the local noise on the channel on the lattice. So if you take the adjacency graph to be the lattice system for the subsystem variance, this epsilon tilde here will be the local noise on the lattice, the local erasure noise on the lattice. On the other hand, if you just take the adjacency graph to be the auto graph, then you'll find that this epsilon will be defined in respect to the erasure noise acting on any d qubits. So you can see that these two-way bounds is just telling you that epsilon can also be a measure of how close you can get after the recovery channel. So as a picture, I will show you that this subsystem variance just gives you a notion of generalized distance. So you can see that this epsilon is a function of B. So in the case of the exact QEC, you can actually calculate epsilon, and you will find that it will be a step function, and you will have jump at D star, which gives you the distance for the exact QEC. On the other hand, for the approximate code, the general behavior will be like this. So you can see that as D increases, the subsystem variance will just increases, showing that the capability of correcting D erasure noise is decaying, and this growing behavior will just give you a rough version of how many of code distance for the QEC code. So this is basically everything about the subsystem variance and how you can deal with the approximate code. Any questions for now? If no other questions, I will just proceed to talk about the quantum circuit complexity and how the subsystem variance will just give you some results about the complexity. So first of all, let's define the quantum circuit complexity. This is for any state, the circuit complexity will just be defined as the minimum number of layers of disjoint 2 qubit, the generator states. Note that this assumption of qubit or like 2 local is not essential here, it's just for simplicity. So the urgency graph also plays a role in the definition of circuit complexity. In the case of complete graph, we are talking about the auto circuit complexity, which only requires that the disjoint 2 qubit to acting on any 2 qubits. It doesn't but it doesn't to be nearby or anything. But on the case of lattice, on the case where the adjacent graph is just the d-dimensional lattice, we will require the gates for acting on the nearest neighbor. So here are two examples of the circuit that we're considering for the O2O case and the 1D case. So here we will state our main theorem, which tells you that when the subsystem variance is small enough, then the circuit complexity will be lower bounded. More precisely, we show that when the channel entropy for the epsilon, when the channel entropy for the subsystem variance is smaller than k over n, where k and n are the number of logical qubits and physical qubits, then we can define we can show that the circuit lower bound of any co-state is larger than log d. Here is defined for the O2O circuit complexity, and so the urgency graph that we use to calculate the subsystem variance will also be the complete graph with O2O collectivity. Here, the notion of delta denotes the robustness of the circuit complexity, which is basically saying that for any state delta close to the co-states, we also have the circuit complexity lower bound. Our theorem can also be applicable for the finite dimensional lattice system. So similarly, the only thing that we need to change is the urgency graph that we use to define the subsystem variance. And when the channel entropy is smaller than k over n, then we will show that the circuit complexity is also lower bounded. So here are some remarks about the theorems. One intuition of the theorem is that the AQC is sufficiently good, then the local indistinguishability will just ensure that the code is hard to prepare. So this is pretty familiar for the exact code, where as we all know, like the Tori code locally indistinguishable, and we know that it's non-range entangled. We need a circuit of steps L to prepare that. And there are some remarks about the theorem that we have. The first thing is that this reflects a universal complexity feature of the entire code space, including superposition of code states, which are important but rarely understood. So know that for usually when people have circuit complexity results is known for a certain state, and we need to require the state to have some properties. But here, the results can be applicable to the whole subspace, and any superposition will work. Another thing is that this error condition are near optimal in some sense. Basically, we can find counterexamples of the co-subspace complexity lower bound just outside of this inequality. Also, this conversely indicates there are some lower bounds on the AQC error. So if we know that the co-subspace contains any trivial state, then we know that the AQC error condition are violated, so the code cannot be too good. Any questions about this result?
I'm okay. Like, I mean, anyone like, yeah, if anyone has a question, just unmute and ask. Yeah.
Yeah. So let me proceed. So I will just give you a brief idea of how we prove this theorem. So the idea is just to use a Nikon argument. This is similar to what Anshu did for proving the NLTS theorem. So the idea is that given some co-states, we're just trying to prove this by contradiction. So suppose that this co-state can be generated from a product state that are circuit with certain depths. We can, instead of running this circuit on that co-state, we are running the circuit backwards on the reference state with the maximum mix state on the co-subspace. So recall that for this reference state, we already know that the entropy will just be k. So it's a large number depending on the dimension of the logical subspace. So suppose that the subsystem variance is small within the Nikon scale. After we run the circuit backwards, we will show that we will see that the output for any qubit will just be close to 0, because we already know that locally the gamma will be very close to any co-state. So since the output of any qubit will be close to 0, we know that the entropy of that output will just be very small, controlled by the subsystem variance. using subadditivity, we can just add up all of these.
But so Jinmin, like, are you effectively trying to, like, find out how much entangled the code states have to be for it to, like, do be able to do approximate quantum error correction?
Yeah.
So basically, you are effectively asking how much entanglement do we need, and like, and to generate that entanglement effectively, you need to have, like, a circuit of some particular depth.
Yeah, exactly. So basically, our result is saying that if the accuracy is good enough, we know that it must be very entangled.
Yes,
Yeah.
exactly.
So
And basically, and not only for AQEC, like you are talking about, like, I mean, because it's a continuous thing, right? So it also says things for, like, a general quantum error correction code, like the exact case also.
yeah, exactly. This is applicable for both QEC and exact.
Yes.
Like exact QEC or AQEC. Yeah.
Very nice.
Yeah. So the final step of this proof is that you just use subadditivity. So if the output of any qubit is just very close to zero, the entropy is very small, the total entropy will also be very small. So but we already know that the total entropy will just be the reference state because this is the unitary, it doesn't change the entropy. So this will lead to a contradiction if the depth is not high enough. So one thing that's worth noticing is that our work is general for any kind of for any depth circuit. So we can our results is not only applicable to make a distinguish between non-range entangled or short-range entangled, but one thing that people care most is that whether the circuit complexity is O1. So whether, like, the code can be generated by constant depth depth circuit. So this is important in, like, phase classifications in condensed matter systems, and it's also related to, like, LTS and quantum PCP, like in quantum information community. So we will just focus on the case of like whether the circuit complexity is O1 here, and our result just tells you that if we want to care about O1 complexity, we only need the epsilon to be 1 over n if the k is O1. On the other hand, if the dimension of the logical subspace is approximately linear, the rate is if the AQC code has a constant rate, then we just need the epsilon to be exponentially small to have a non-range entanglement. More precisely, we can show as the circuit complexity phase diagram here. So here, when epsilon is sufficiently small, the code will just lie in this non-trivial region, meaning that any code subspace will have a super constant circuit complexity. On the other hand, if the code lies in this unboundable region, we can show that there exists some AQC code with trivial circuit complexity. Here, we give another phase diagram in terms of the accuracy and accuracy. We can see that the accuracy and accuracy doesn't give you a very clear boundary between the unboundable and the non-trivial region. So this is kind of suggesting that the subsystem variance that we define is more clear notion of the circuit complexity, that is a more clear notion to characterize the circuit complexity for the AQC code. So here I will talk about some examples where our AQC idea and theory can be applied. So it has been known that for the thermalized system, if you pick some energy window from the system, it can actually be a pretty good code with exponentially small error. And our result can show that any state in this energy window must be highly entangled. On the other hand, if you consider a random unitary code, or similar things can also be obtained. Also, in physics, people talk about a lot about topological code and CFT non-range sectors. I will talk about this more in later this talk. Also, there are other codes that we construct that falls in the unboundable region, and our results can also provide you with some notions of complexity for this kind of code. So if any of you guys are interested in these details of this kind of codes, we can talk about this later. So that's basically the result about the circuit complexity and the HVC. And if there are no further questions, I'll just move on to how this can provide you with insights in physics. Okay, so
by the way, that random unitary code, is it like what is that? Like maybe is it like the encoding circuit is somehow random unitary?
yeah, exactly. I just pick some. I just have a logical state tensor with some like product states. I apply a random unitary to that. I consider that as an encoding. In the end, you'll find that the code is pretty good because, as you can imagine, the logical information just spread out to the whole system, and you can actually calculate the epsilon. You will find that it's exponentially small. Yeah, basically as you said, so it's a random encoding. Yeah, so let's move on to the physical implications here. So one universal physical insight I want to emphasize here is that the HVC just can provide you like the knowledge subspace of physical systems are associated with the interesting codes. And if you just regard the knowledge subspace as the HVC code, calculate the code property, it'll give you some information about the physical system. So two cases that we have application with is the gap states and the gapless states. For the gap states, people have already studied a lot about the topological order. Everyone is familiar with the Tori code. We know that it's a good HVC code. But in quantum spectral community, a central question was like, what kind of features of quantum systems are associated with topological order? So if you are just consider a general Hamiltonian, you want to study the property of its ground state subspace, it's not always exactly solvable as a Tori code. So there are three notions of topological order. The first notion is just the TQO, topological quantum order. This is basically a code condition for the ground state subspace. It just says that the code has a macroscopic distance and exponentially small error. So one can also show that this guarantees that the whole Hamiltonian is stable under perturbations. Also, people have two other notions. One is the non-range entanglement. People usually say that a topological order is one system with states that cannot be prepared by finite depth circuit, or in our language, a state that has super constant complexity. Also, people have the entropy condition where you can calculate the topological entanglement entropy, and it's related to the violation of entanglement error law, and it can give you information about the anion data. So there are three notions, and one issue is that although they are widely useful in different situations, the relationship between these three notions are not well understood. On the other hand, our results can actually provide you a way to understand the relation between the three notions. So the first notion is the TQO. We know that this is basically saying that the ground state is a good code, and people usually argue that even if you add some perturbation to that, this is saying that the subsystem variance is exponentially small. On the other hand, our results can directly give you some understanding of the circuit complexity of the ground state. As shown in the main theorem, to have a non-range entangled state, we only need the ground state as a code to be polynomial small. More precisely, we need epsilon to be smaller than 1 over n. So this is drastically different from the requirements of the TQO that the ground state has a exponentially small subsystem variance. Also, the topological entanglement entropy, so it's defined as a correction of the error law for the entanglement entropy on some subregion A. So here, for topological order system, you can just take some subregion A, you can calculate the entropy. The first term is basically the error law. There's a constant correction, and the gamma will just gives you the topological entanglement entropy. So our result shows that if you just consider NK code defined on a 2D lattice on a torus, Suppose that epsilon is 1 over n small for any contractual region of linear size, then all cosets have a non-trivial TE. So specifically, you can actually show that the abelian topological order saturates the best TE in lower bound from our approach. So the takeaway here is just that our results can show you a gap between 3 notions. The TQO is very strict. It requires the epsilon to be exponentially small. We show that the notion of non-range entangled and topological entanglement entropy can be much more relaxed. We only need the epsilon to be polynomial small. As long as it scales with 1 over n, this property can still hold. So this suggests that there must be something in between. So maybe we can cook up some models that's polynomial small in the epsilon, but still has a non-entanglement or TE. For the critical systems, they are much less understood from code perspectives. Here we just consider the non-energy sectors of the critical quantum system, where the cosets are just CFT states. This is very important from the perspective of ADS-FT because people talk a lot about how ADS-FT can be understood as a quantum code, but the most understanding are based on some toy models, for example, the happy code, which are like exact codes, but we know that they don't actually capture the behavior of the CFTs. So our work is the first work to actually calculate the code property of the CFT. And the result is that for small d up to some log n distance, we can show that the code property will just have a polynomial scaling. So here we show that epsilon is n to the power of minus delta over d. The delta is the minimal scaling dimension of the CFT, and the d is the spatial dimension of the system. So this is very interesting because you can actually find that it lies on the boundary of our complexity results. So it's not exponentially small, but it's by tuning the CFT that you are considering, you can tune the system from the trivial region to non-trivial region. So this is a very special feature, and you will find that most of the approximate code that you construct cannot either have exponentially small error or like some trivial like O1 error. So this can also have give you some complexity implication for the CFTs. Although we all know the CFT states are non-range entangled, but that's defined with respect to the lattice systems. In this case, our results can show you that if you consider CFT with delta larger than d, then you can show that it's not just non-range entangled, but it actually has an auto-circuit complexity in lower bound. Actually, this CFT can be found. For example, you can consider a monster CFT, and it's related to ADS-FT, and you can find that the delta is larger than d in that case. So let me talk about some future work that I'm planning to do. The first thing is a more detailed classification of the unboundable region. This is actually an upcoming work where we look into the region where we thought to be unboundable, but we can find some intrinsic structure there. Also, we can consider like generalization to the continuous variable case and the fermionic case. Also, in condensed matter community, people talk a lot about like mixed state phases and how they can be like it's natural to sort of the mixed state phases. There are some error correcting codes and see like whether there are classical or quantum information stored there. Also, one can think about the AQC properties of general many-body systems and see like how our AQC results can give you some information of the systems. So here are some take-home messages that I want to emphasize. The first thing is that the subsystem variance will give you a phase diagram for the AQC related to the circuit complexity. Here's the phase diagram. In the orange region, all of the cosets are non-trivial. And this can also offer you a tactic to prove in circuit lower bound for any state, because one thing you can do is just you pick some states, you try to cook up some other state that forms a code with that, you calculate the epsilon. If epsilon is small in the non-trivial region, you can prove the circuit complexity lower bound for both of the states that you're considering. A second thing that I want to emphasize is that the no-energy sector of many-body system can be interesting codes, and the accuracy can provide new perspectives in many-body physics. So it's deeply related to complexity and entanglement properties. It can give you complexity results for many-body systems. It can give you entropy lower bound for the many-body systems. And that's basically everything for this talk. And any questions are welcome. Thank you so much.
Yeah. Thanks, Jinmin. This was very nice, and yeah, I mean, very excited for all these future questions, and also I'm personally more interested in for Flowcate.
Yeah.
I think this distance thing is a bit non-trivial, right? Because distance in Flowcate, itself, I mean there was a paper how to have define the notion of distance in Flowcate codes, and then you gave us kind of a distance notion, where you went through this erasure errors and more of a continuous notion and so on. And it's nice as all these things connect with entanglement and give bound on circuit complexity and so on. So yeah, quite amazing. And then yeah, I think
yeah, thank you so much. And I'll be happy to discuss about the Flowcate direction more later.
Yeah. I mean, definitely. I think if we start some project or something related to that, I will be more than happy to include you. We can have some meetings and we can chat about it. I think it seems it seems a nice direction.
Yeah. Thanks. I'll be excited.
Good. Yeah. So yeah, if anyone has any question, please unmute and ask.
Yeah, so I'm just wondering about your circuit complexity result on this so you have this two theorems, right? So one is where you have all-to-all connectivity, and the other one you have this lattice
Yeah.
So I'm just wondering, what about just arbitrary graph, is there a general result for just arbitrary
the general
graph?
result. Yeah, in the general results, the only thing you need to change is that you need to calculate the subsystem variance for that graph. You swap the G here to that graph, and we can prove that the circuit complexity is larger than a function of D. So the function will just be the inverse of so I didn't write this down. So for example, if you can when you have a notion of graph, you can define the size of an icon under some depth T circuit. You define the size of the icon to be Ft, where T is the size of the circuit. So
sorry, the size of what again?
The size of the circuit. So you can consider a depth T circuit with respect to that graph that you want to deal with, and Ft is the size of the circuit. So we can prove that the circuit complexity is lower bounded by F inverse D.
Oh.
So
okay.
yeah.
So how do you determine this function though?
Yeah. So the idea here is that it's from this picture. So we want to use the subsystem variance to bound the entropy of the output qubit. So we want to consider a region where if you run backwards with the circuit, it will just give you one qubit. So basically, this will just be the size of the circuit under that T, right?
Right.
Yeah.
Okay.
So yeah, but we only have information for the subsystem variance with size D. So the circuit, so this will just give you an equation like D equals to Ft. So the circuit depth that you can have information will just be like F inverse D. Yeah, but well, these are all technical details. But the thing that I can say is that for general graph, we can also have a theorem similar to the previous version, and all these results doesn't. Let me Wait, sorry. Yeah, this one. This one doesn't rely on the urgency graph. So basically, here, if you want to define whether the space is non-range entangled or short-range entangled, we only need to switch the epsilon to be defined with the urgency graph that you want to consider. And as long as this is small, you can show that the circuit complexity is non-trivial.
Okay.
Yeah, so you just need to redefine the subsystem variance in this case.
I see. Yeah, regarding to the flowcut case, I'm just wondering like how do you like properly define like this generalized distance? Because like you want to kind of like define it over space and time, and I just thought like that would be like very interesting.
Yeah, my intuition for the flow K code just come from the exact example, so I'm not so sure like whether that also applies to the.
And basically, like, instead of circuit maybe one needs to think about something like spatio-temporal object, like more general, so yeah, so you need to maybe think about like some lattice. Let's say if you have a lattice in in space and time, and
Yeah.
then there maybe like try to define such a such a notion of this subsystem, like this subsystem variance. And yeah,
Well,
right.
yeah. I don't know. I feel like you can still define it in the same way, right? You just consider some
Yeah,
erasure.
Jimin, I agree. That's one way. Like you can just like add a T, like as you said, like treat
Yeah,
each of the code space different. And yeah,
yeah,
but I
yeah,
was
yeah.
thinking like even more like whether, because at the moment you are giving bound on total number of basically the circuit complexity,
Yeah,
like effectively through entanglement. I was thinking like maybe if let's say if you take time also axis also into account, maybe now you have like a more exotic structure.
yeah.
And then I don't know, like the people call it dynamic entanglement, like could come into picture. So you have like this time also, and I was thinking some of the stuff that people have studied in in dynamical entanglement theory, whether I don't know like what it would be like. I'm just dreaming at the moment, like trying to think whether whether we can use some of those tools. Like so, I'm thinking a tool such as, I don't know, from comps or something like could be
Oh,
used to uh, give a more general notion here.
I see.
Because here you're looking at like a very static object, like but now I think I was thinking like, yeah, like overall, like in your bound, like circuit. So one has to generalize this notion of circuit complexity. Maybe it has to also include the number of time steps in the complexity. So it's like this generalized circuit complexity, and maybe everything generalizes, like
I
I
see.
don't know.
That's your point.
I don't know.
That's your point.
I don't know.
Yeah, it sounds very interesting, but yeah, I don't have any clear thing in my mind.
So by the way, just something I have in mind. So this should be you should be able to use this for like space-time code directly, right? Because it's basically like like you get like just kind of like a subsystem code from a
Oh yeah,
space-time code, right?
yeah,
I
yeah.
know
I
what
was thinking
would
about this.
mean though, but
Yeah. I don't know. I think this should be applicable for like the subsystem codes, and but I haven't tried to figure that out like in detail. I guess there's some subtleties for the subsystem code because like no you have the gate qubit and locally there could be like other things happening. But yeah, I don't know. It might be worth exploring.
Mhm. Yeah, that'll be interesting.
Yeah.
Okay. Okay, so I will stop the recording now.
Yeah.
We let's thank Jinmin. Like thanks Jinmin for this nice talk. Yeah. So let me stop the recording.
Thank you
Uh,
so much.
yeah. So